Okay, so what we want to do in this period is, one, go through those special examples that I've asked you to think about. I'll do that very quickly. So one, I asked you to investigate the natural log of x. The natural log of x near x is 0. And so if you get a GDC and you graph that thing, you're going to know that it looks something like this, and it goes way down. And this point right there is the point 1, 0. And so there might be a lot of questions about, like, why. Well, so if y is e to the x, then when x is 0, y is 1, and so the inverse function must go through 1, 0, and so that's just right there on that map. And then we're looking at other things. As x gets big, e to the x gets really big. Okay, that's good to know. And so now, what happens with the natural log of x? Well, so remember that these things are inverses to each other, so it just is a flip over that line. So here's e to the x going like that, and I know that these things are flipped over there on the line y equals x. So I know that as x gets big up this way very quickly, the natural log of x gets also very big that way. Now let's think about as x gets big and negative, e to the x gets close to 0, and it can't touch 0. So then when we look at that red line, that means that the natural log of x also can't take x equals 0 and must go way down, so towards negative infinity. Okay, so just doing that, we're kind of investigating what happens when I get close. And in this problem we had to use a picture, but you could also use your numbers on your GDC and plug things in and find out that the closer we are to 0, the faster it goes way down. And there's another way to investigate that, which is for x less than 1, we can write x is equal to a over b, where a is smaller than b. That's what it means to be less than 1. And so the natural log of a over b is the natural log of a minus the natural log of b. And since a is less than b, the natural log of a minus the natural log of b is less than 0. And as b gets big, the difference of the natural log of a and the natural log of b, gets quite big, that it gets to be a very large number, negative large. So that's what's kind of happening here, and this is part of that investigation that we want to think about. Now, we had the same idea with tangent. I want the tangent of x near x is pi over 2, and we remember that the tangent of x is the sine of x over the cosine of x, and the sine of pi over 2 is 1, and the cosine of pi over 2 is 0. So therefore the tangent of pi over 2 does not exist. That's what DNE here means, does not exist. So the tangent of pi over 2 doesn't exist, and that means if we want to know what happens at pi over 2, once again, we have to explore. And so with some calculator use or paying attention to the book or whatever it is, here's pi over 2, we find out that tangent goes up real fast and negative pi over 2 is down real fast. And then the next question would be, well, what happens next? And we find out that tangent makes the same picture again because it is periodic, and that means when I am going towards pi over 2 from below, the thing shoots way up, and when I'm going to pi over 2 from above, it shoots way down. So this big idea here is important to investigate both sides. So then finally we had that last question, which was, I wanted you to investigate cosine of x near pi over 3. But we know cosine of pi over 3. The cosine of pi over 3 is equal to 1/2. And so you'd say, oh, well, you know, Mike, Mr. Corey, there's no problem at pi over 3, so what? And so there's this idea here that this function is nice and smooth. Cosine, remember that it starts high and it goes back down. And so when we get to pi over 3, it's just right there. And when we're looking at cosine, it goes down that way real nicely, and it comes up way that real nicely, and there's no problems here. So when we get real close to pi over 3, both from the left and from the right go to 1/2. So that's another idea that we're going to want to talk about. Okay, so that was the problem set that I asked you to investigate, and that's all there is to it, really. But we're going to take these ideas and we're going to tie them all together. And we're going to give them a name, which is called taking a limit, or finding a limit. And so I don't want to have to keep on asking what happens when something goes near something or whatever. We have convenient notation to write, so limits. When I want to ask what happens to the function f of x when x gets close to a number a, we write the limit lim as x goes to a of f of x. So this mathematics is the same as that question. What happens when I get close to a is the same thing as writing it just like that. So that's a really convenient notation. And so, for example, the limit as x goes to pi over 3 of the cosine of x is 1/2. And because in all the directions that I go to from x smaller than pi over 3 to x bigger than pi over 3 and back, cosine just does one thing, it goes to 1/2. But if I said the limit as x goes to 0 of 1 over x, we say that this thing does not exist. And again, I'm going to write that as d and e from here on out. And the question would be, why not? And so then we remember that picture that we drew the other time, and the picture that we drew other time went this way and went this way. And you see that near 0, over here it goes down, and over here it goes up, and these things don't do the same thing. So don't do the same thing. And because it doesn't do the same thing, that means it's not working. It doesn't have this limit. We're going to say, by definition, the limit doesn't exist. So we say a function f of x has a limit near x is a if the limit does the same thing on both sides. Okay, so there needs to be a way to denote that, to write that in an easy way, and we're going to say that the left limit, another way to say that would be lower, the lower limit or the left limit is going to be written as the limit as x goes to a minus of f of x, and a minus here means that x is less than a and x goes to a. Let me be careful about writing that x. And so the right limit, or upper limit, is the limit as x goes to a from above of f of x. And that means a plus is x bigger than a, x getting smaller to a. And so a limit exists, f of x has a limit if the limit x goes to a from below of f of x is the same thing as the limit as x goes to a from above of f of x. And so now that cosine idea makes a lot of sense, because if I choose numbers bigger than pi over 3 and I get closer to pi over 3, cosine just goes to 1/2. And if I choose numbers smaller than pi over 3 and I get closer to pi over 3, then cosine just goes to 1/2. So the left limit and the right limit for cosine at that number match, and therefore the limit exists. Nice and easy. But for tangent and 1 over x, the function doesn't exist at pi over 2. 1 over x doesn't exist at 0. Tangent doesn't exist at pi over 2. And the closer I get to 0 or to pi over 2, we find out that the direction that we move on matters. So remember that as we get closer to 0 in 1 over x, if I'm less than 0, it goes to negative infinity. If I'm bigger than 0, it goes to positive. And when we were looking at tangent, when I was less than pi over 2, it goes to positive infinity, and if I'm bigger than pi over 2, it goes to negative infinity. So it is important that we pay attention to the direction that we're moving. Okay, so now let's go back and let's think about that function g of x. G of x is the function x minus 1 times x plus 1 over x plus 1, and minus 1 there. And my question was, what happens to g of x near x is 1? So another question is, what is the limit as x goes to 1 of g of x? That's the limit as x goes to 1 of x minus 1, x plus 1 over x minus 1. And so now there's this really, really big important thing, that using limits, we don't need to use numbers. I'm sorry, let's not say use numbers. Use the number given. Use the number given. So in this case, that number is x is 1. So remember, when x is not 1, g of x is just equal to x plus 1. Okay, so now I've got the limit as x goes to 1 from below of x plus 1. These are all the numbers that are less than 1, but we're getting closer and closer and closer and closer to 1. And as we get closer to 1, this guy just goes to 2. It's a little bit less than 2, but it gets close to 2. And now I have numbers x goes to 1 from above. These are numbers bigger than 2, x plus 1. Sorry, these are numbers bigger than 1, so the sum is bigger than 2, and it gets closer and closer and closer and closer, and ultimately it goes to 2. And so we say, oh, hey, look, the left limit and the right limit are equal, and so we would say that the limit as x goes to 1 of g of x is 2, even though g of 2 does not exist. So the reason why this is very important is now suddenly we can investigate what's happening to a function even when we can't use their numbers directly, and that's why limit is an incredibly valuable piece of mathematics. Okay, so the limit at a point says investigate what happens to the function before the point and after the point and get very, very, very close. How close? As close as you want, infinitely close, but you can't equal the point. We can't always put it in. Now you might say, oh, but Mr. Corey, in this problem, like cosine, I can just put it in, and in that case, usually that is enough that you just say, okay, well, I put in the point and we're done. But it doesn't always behave that way, and in class we can investigate those little bit weird guys. So hopefully that gives you kind of a basic idea of what a limit is. We will try a couple more. In fact, I will give you some homework, and you can investigate what limits are in that way. So, let's see. Why don't we also investigate a little bit about limit at infinity, but I can do that coming up. So here's what I'm going to do. I will put in some homework for you. It'll be a PDF or something like that, and then you can give this a try, and then in the next lesson I can go through some of those ideas. Thanks so much.